It's getting hot in here. So, no, we're not doing that. Folks, this episode is going to be about how to keep your home cooler. And I know we're in the winter time, so I don't know, maybe save this and come back to it when it's summertime. Anyways, keep your home cooler. Do it in a way that's better for the environment. It's a good one. Let's get into it. All right, peeps, welcome back. Today we're talking about cooling, as you probably already heard. Specifically, we're talking about radiative shields for cooling down your house, and this is coming straight out of Penn State. Now, I got some beef with this topic. We're going to go back a couple years.
Why do you hate radiative cooling of buildings?
I hate radiation, and it's saying something because I loved heat transfer. I love thermodynamics. It was one of the best classes for me. I got an A. That was one of the best performances I had in undergrad. But some years ago, I did an interview with Apple for a product design engineer. And the very last question, it was, how do you cool down a Mac? Like went back when the whole Mac wasn't a screen.
Mm-hmm.
And I'm like, easy, like conductive. Like you touch the metal to the processor and you get the heat out. And they're like, great. And I'm like, you do forced convection. You got some vents. You push some air through it. Great. And I'm like, yeah, that's how you would, reasonably cool a Mac. And they're like, there's no other way. I'm like, no, like I've never heard of another way. And they're like, are you sure there's no other way? I'm like, yeah, of course. Like there is only two ways you would do a Mac. That's the only way you could cool it. And they're like, really? I'm like, yeah. They're like, all right, great. We'll talk to you later. And then 2 minutes later, I got a rejection. And it wasn't until after the fact that I'm like, you idiot. They don't care about like what is feasible. They're saying, do you understand the three modes of heat transfer? Radiation
and what are those three
is
modes?
The last one. Conduction, convection, radiation. And they made sure I never freaking forget it.
No, this is taking me back to me not being able to let go of the fact that I missed the word infallible and the spelling being third grade because I thought it was spelled with ABLE at the end instead of IBLE. But I can understand your pain here, right? And it is the often forgotten method of heat transfer. Beyond conduction and convection is radiation. Yeah. And it's really interesting that they use radiation, or they're planning on using radiation here to cool buildings, right? Traditional cooling systems rely heavily on conduction and convection. They don't necessarily rely heavily on radiation. So your traditional cooling system using refrigerants and electricity, right? That an AC system, these are bad for the environment. They consume a lot of energy. They
How
rely
much
heavily.
Energy? Do you know? Because I got some stats. I said,
Yeah.
How much energy? Do you know?
Hit me with them.
All right. It accounts, so just HVAC, cooling, accounts for 10% of global electricity consumption.
Crazy.
I feel like that's mostly the US because I've been to Europe and AC is not a thing. So that's mostly, us. And I guess Asia too, honestly. And then you have CO2 emissions. Globally, HVAC cooling accounts for 7% of CO2 emissions, which is almost on par with concrete. And that's crazy.
And is both in excess of the entire United States country emissions, which is crazy. Yeah. So, we're using all this energy to cool buildings. Can we come up with a new method? Maybe that doesn't necessarily replace it, but even if it just helps, right? A new method that doesn't actively use electricity to help with the cooling. So this research team from Penn State designed a special plastic sheet that they can put on top of buildings, and it helps cool the buildings using radiative cooling, which, it's kind of crazy to understand this, but when an object is very, very hot, if the conditions are correct and the material is correct, it's able to emit waves of radiation similar to the light that comes and hits you from the sun. The heat from the sun, that's radiative heating. Buildings, in this case, with the special plastic sheet on it, can emit heat using radiative cooling. It emits waves of radiation, which reduces the temperature of the building and lightens the load on the HVAC system.
I'm going to be honest with you. I just think of it as building sunblock, right?
Yeah.
Like I go outside, I put on sunscreen, to make sure that those pesky UV rays don't age me too quick, right? I'm already suffering from the eyes. I can't have the rest of the face go that way. So now these folks over at Penn State, it seems like they've been cooking up something similar. And what's interesting, this is the first I'm hearing about radiative shields for building applications. But apparently it's a area of research that there's been a lot of effort from different universities, different industry partners, and they've usually focused on shortwave infrared light. So like in the wave light spectrum that the sun emits into your home or into the world, there's the visible light, which we can see from morning to night, and then there's that shortwave infrared light that's coming through, and you're not able to see it, but it is actually heating up the environment. What's interesting is that this shortwave infrared light is really good at being absorbed into like bricks and other building material, but the typical glass that you have to like look outside your window actually blocks it out, which is not the case for visible light. And a lot of these other folks outside of Penn State have focused on making sure that they're shielding against those SWIRs.
Well, and what's awesome here is, in addition to that, right, in addition to just shielding light and reflecting both visible and infrared light, which are the things that can cause a building to heat up, right? We mentioned this. They're also a passive radiator, which means that they help release heat that's trapped in this building into the atmosphere. Specifically, this phenomenon mostly happens at night, but because there's no new radiation coming in from the sun when it's dark out. But this already happens on Earth. And if you want a very pertinent example to help you understand this, or maybe to believe me that this phenomenon happens in general, have you ever noticed on your car, the warning will ding that there could be frost on the road if it's 39 degrees outside, even though 32 degrees Fahrenheit is the freezing point of water? Have you ever noticed that? 38 or 39 degrees, my car dings to remind me that there could be frost on the road, or there could be black ice.
My car is too old for that, unfortunately.
Well, just my car is also from 2013. I think it's just German.
There you go. Yeah.
But that being said, right, so it's possible for there to be frost or black ice on the ground, even when the ambient air temperature that night never reaches freezing. And the reason that that's happening is because the Earth's soil is able to lose energy, to emit heat into the atmosphere via radiative cooling. So essentially this phenomenon already happens in the Earth. The Earth's soil collects heat all during the day, and then at night the Earth's soil releases that heat as radiation into the atmosphere. Specifically, it's able to happen really, really well with long wave infrared radiation, because it's able to permeate through the air and make it all the way out into space. So Earth is able to release heat into space using this phenomenon when the light isn't shining on it from the sun. They created material that helps buildings do that significantly better than they would do on their own. It helps buildings release heat at night as infrared radiation, which is pretty crazy.
See, this is why I'm happy one of us was paying attention in biology, because of these fun soil facts, which I definitely did not know about.
Well, I'm not going to lie. This wasn't a soil fact. This actually came from me paying attention, because at one point I was speaking with the founder of a startup that's doing something pretty similar to this. So shout out to Sky Cool Technologies, which is the one who gave me this crash course lesson, the things I should have paid attention to.
Dang, okay, that's awesome. But okay, that's actually a good segue into, well, what is this material that these folks are building, and why is it so amazing? At the basic level, I think we already called it, but it's it's a plastic shield, and this plastic is made out of powdered polymethyl methacrylate. I think I said that right. PMMA. There we go. Never make me say that again. And they're fusing it together with their partner, I think, based out of China. Am I right? Because it's an international effort.
So.
Yeah. And they're using fusing, selective laser fusing. Am I right in that?
I think it's powder sintering.
Powder sintering. Okay. Yeah, powder sintering to create these sheets that are porous. The
Not
porous
to like not to interrupt you here, but I also worked on a powder sintering project at
Oh,
Formlabs,
just brag.
which
You know
is
what?
why
You take
this
the
is
mic. You
which
take
is
the
why
mic
this is top
one.
of mind for me. But yeah, actually, it's one of the same issues we dealt with when we were using selective laser sintering to sinter nylon powder to create parts. Is we were trying to overcome it as a potential issue at the time when I was working at Formlabs because it creates
Voids.
a lot of pores in the material.
Yeah.
Essentially, you're taking powder and you're hitting it with a lot of energy, heating it up until all these powdered bits bond to one another to create one giant part. During that heating and melting and fusing process, it generates a lot of tiny pores, a lot of tiny air pockets in the geometry, in the microgeometry, and even in the macrogeometry. You can look at it with your naked eye and see it. It creates a lot of pores, lots of air pockets. And for some people wanting like a 3D printed part that's nylon, that's super strong, they don't want porosity, which is why Formlabs is trying to figure out how to modulate that. But in this case, the tiny little pores, the tiny little air pockets, they help with insulating a building, and it actually helps with scattering visible light to make sure that it can bounce heat away as opposed to absorb heat into the building when the sun is beating down on the building all day long.
Yeah. And that's the core of the secret sauce. And in terms of like, well, does this thing work? Which I think we've already spoiled it. It's a yes. I think the follow-up question there would be, how well does it work? And they did a fun little experiment. You should definitely go on the article and look at the picture they posted because they use like an IR sensor. They're outside. The ambient temperature is like 80 degrees. The sun is just beating down. And they have this thermometer that is inside of a box made out of cardboard. One that's just sitting out. And then one that's in this PMMA shielding material that they developed. And it's honestly quite impressive, man. You have 80 degrees outside, 73 degrees in the cardboard box, so not too bad, but then 65 degrees in the PMMA shielding environment, which is quite substantial. And the feedback that they gave is that PMMA, on average, reflects 80% of the visible and infrared light. So, I don't know. I feel like if I was working somewhere in the summer, and I don't know, I was serving ice cream or I was working in an environment where I was exposed to, you know, the outside ambient temperature, I would want whatever building I'm in to have some of the shielding on it.
Yeah, I'm with you, right? And the awesome thing here is it doesn't require any additional electricity draw. You know, there's no, it's not stressing the grid, right? And we talk a lot about, like, is our infrastructure strong enough to keep up with increasing energy demands? This is something that doesn't create additional energy demand on our grid. It actually reduces the energy demand on the grid. Imagine being able to keep the indoor temperature of this box, right, 14 Fahrenheit cooler, lower, not just than the other box, but lower than the outside air. So it's like just having this shield on top of your building. Imagine, you know, hoping that the same heat transfer principles of the tiny box apply to a giant building, right? Because it's the amount of infrared radiation it's receiving is proportional to the surface area of the ceiling. Say you've got a giant building, and without using any AC, when it's 80 degrees Fahrenheit outside, it can be 65 degrees Fahrenheit inside without paying for a dime of electricity for air conditioning. That's the potential benefit offered here. Or imagine when it's 100 degrees Fahrenheit outside, you don't have to use the AC to bring it all the way down from 100 degrees inside your building, or hotter, because it can get hotter inside than the outside temperature with all the radiative cooling, greenhouse effect, essentially. Instead of bringing your building down from 100 degrees Fahrenheit down to 70 degrees, whatever is your comfortable room working temperature, you can let this radiative shielding and radiative cooling do half of the work, right? Or brings it down a considerable amount. So then your power draw and your electricity bill is a lot lower.
Yeah. It sounds great on paper, but I will play devil's advocate for just a second. I will say, for a technology that's meant to be eco-conscious and very friendly. It is kind of a downside that it's made out of plastic.
Yeah.
And it is kind of a downside that after a couple years exposure to sunlight, it does degrade and lose its, let's say, potency and has to be replaced.
Mm-hmm.
So, the energy input to manufacturing and maybe potentially recycling, installation, removal, all that has to be factored in already. But since you're putting it outside, it also gets exposed to the environment. As it wears down, it's going to get, washed down into the soil, into the water supply. Microplastics are everywhere. They're in us as we speak right now. Those are some of the downsides. I figured it's worth pointing out.
No, I'm with you.
Still hopeful that as, they've planted the idea here that you can have structures with voids in it to do all this cool thing. I'm hoping that material science advances enough where we can have something that, lasts longer, is made out of more eco-conscious material.
Right. Yeah. Something that won't degrade and require replacement. One thing that they mentioned is like, oh, this is cool. Like, it can be recycled, ground up and recycled, and then used again. That's pretty awesome. But I wonder what the minimum requisite, like, virgin percentage of material that is fresh and not recycled. I wonder if there's any difference in potency there if you used 100% recycled material. Also, that I am with you on the concerns around like water runoff. Like, we don't want plastic coating every single building and then more microplastics just making their way into our water supply. That being said, I love the principle here. I'm with you. Like, this should inspire more people to spend effort and time and research on discovering radiative cooling materials that can be used in sustainable building design. Maybe it's just some type of additive that you add to the concrete when you're pouring the roof of a building, that causes it to have this like cool, wonky, porous structure that is great at reflecting light. And maybe that gets you a part of the way there. I'm not sure, but I'm with you. This is a cool proof of concept. I'm excited to see if they're able to make an impact on reducing our energy demand, protecting the grid, et cetera, et cetera. But I'm with you. I also want it to inspire more radiative cooling materials and better radiative cooling materials for future building design.
Dude, amen to that. What do you say we wrap it up?
Yeah, let's do it.
All right. Well, folks, we have an international research team that's co-led by Professor Akhilesh Lakhtakia from Penn State. And they've developed a porous polymethyl methacrylate, or I'm just going to call it PMMA, sheet that can radiate heat into space. Now, these quarter-inch thick sheets reflect about 96% of visible and infrared light, effectively radiating all the heat that's been accumulating in your house or about to enter your house back into space. In all the tests they've done, they've reduced interior temperatures by approximately 14 degrees Fahrenheit compared to outside temperatures when the outside temperature was like 80 degrees, which is quite substantial given that, traditional cardboard materials or construction materials could only do something about 7 degrees. This innovation offers an energy-efficient alternative to traditional cooling systems, potentially decreasing the reliance on air conditioning. And that's important because cooling is responsible for about 10% of global electricity use and 7% of our total carbon emissions. So this technology is not only going to keep your home cooler, but it's going to do it in a way that's better for the environment.
Money.
Thank you. All right. That's the pod.
Peace.